Hello, and welcome to the second annual Dyndrite Developer Conference. I'm Kristen Mulherin, and I'll be moderating this two-day event as well as the closing roundtable tomorrow. A reminder before we get started, please use the Q&A at the bottom of your screen to submit your questions for each speaker. We have allowed time at the end of each talk to address your questions. We have an impressive lineup for you today. We'll be starting off with Harshil Goel, the CEO and founder of Dyndrite. Then we'll hear from SLM CEO Sam O'Leary with the industry keynote, followed by a fireside chat between Sam and Harshil. After the break, we'll hear from the CEO of Essentium and some short presentations from Aconity 3D, ExOne, and the CTO at Impossible Objects. But first, we have a short video to share. With that said, let's get started.
We still seem to be dealing with some of the same software limitations, back to the beginning. We need to be able to think about things. We need to be able to a mass production basis, on a mass production basis, graduate to additive level of efficiency that we see in some of these other more traditional technologies.
The future of additive is production. HP has decades of experience. HP has decades of experience automating business cards, printing industry books, from business cards. Our tools at their core need to be able to support massive amounts of data, process data. This is why HP's collaboration with Dyndrite is so important.
Dyndrite's mission is to fundamentally Dyndrite's geometry is created, transformed, and transmitted, transformed, just as PostScript just as PostScript and the Motorola 60 desktop publishing enabled the desktop publishing, Dyndrite and GPUs digital manufacturing. Imagine the wonderful things that people will create, the lives that will be improved, and where humanity will go as a result of this. Is the promise of additive manufacturing.
The companies that will dominate manufacturing, choosing their technology over the next 24 months. Choose wisely.
Please welcome founder and CEO of Dyndrite, Harshil Goel.
Thank you all, and welcome to DDC 2021. It's my pleasure to have all the attendees, the speakers, and DDC members attending today. A number of people ask, why do we even throw this conference? The idea of this conference was to not just highlight, of course, what we're doing over the next year, but to highlight the aspirations, the challenges, and the new technology that every single DDC member is bringing forth. The idea was to work collaboratively and figure out ways to solve real problems and real challenges for all of our collective customers. As you can see, we have an awesome lineup today, ranging from machine manufacturer CEOs like Sam O'Leary and Blake Teipel, all the way to computer and hardware manufacturers like Sean Young from NVIDIA and Brent from Ansys as a software vendor. The idea is to bring together machines, software, and materials all together to make something kind of awesome happen. So the existing DDC members has been steadily growing over the last, I'd say, about 12 to 18 months. We've been steadily adding new types of folks, from software and hardware to even new types of machines and processes. So with that, I'd like to formally welcome our latest two members, Czar and Essentium. I believe these are two key and pivotal members because everything about why they're joining has to deal with production. Production for binder jetting and improving processes, enabling newer and more sophisticated toolpaths production in an HSC environment, allowing you to print much, much, much faster. And at the end of the day, if additive is going to grow and evolve, as Greg Moore said earlier, we have to go to production, and we have to codify our practices. So what is Dyndrite and what's our mission? As you saw in the video, our goal is to fundamentally change how geometry is created, transformed, and transmitted on a computer. And the idea here is that the existing software just simply is a bottleneck to most of the processes that we have. You'll see it as a recurring theme in not only my talk, but a variety of talks. And the idea here is, can we get software that dramatically changes the performance of additive so that additive manufacturing can actually level up, to provide, the ability to solve for a new ocean of possibilities and to push the boundaries that we're all, I think, struggling with from a productivity and scalability standpoint. We've had kind of an awesome year. I'm not going to refer to the elephant in the room, but a lot of things have happened over the course of the year, right? We, for example, have been signing multiple long-term contracts to slowly become an industry standard and leader. HP announced its entrance into software via the HP Universal Build Manager powered by Dyndrite. I encourage you to check out their website via their direct link or our website and get on the beta list. NVIDIA has been steadily pumping out GPU after GPU and new chip after chip, steadily improving literally what it seems like every 6 to 12 months. So in other words, if we at Dyndrite didn't even do anything, the software is getting 2 to 3, 4 times faster every 1 to 2 years. And then, of course, we threw 2 investor days. In light of the current events and situations, right, it was our idea to figure out a way to give back to the industry by pooling together our network to honestly help fund and help all the startups in the space. So between everything that's been going on, I mean, it's been kind of an awesome year, and I'm really looking forward to what's about to happen next. So the crux of my talk is going to be actually focused on raster-based processes. Basically, as everyone knows, binder jetting and raster-based processes like DLP, SLA have been on the rise. And the idea here is manufacturing needs to be enabled by software and compute. So what does that really mean? It means that the manufacturing, we're at a unique point in time where the manufacturing hardware has actually surpassed the software. We have machines that can print at a higher resolution than most software can even make. We have machines that can print faster than you can do build prep. And we have machines that can print all kinds of parts that no piece of software can even necessarily even design. And this all stems from 3 key concepts. So on the raster side, we have one key kind of industry standard, 1-bit monochrome, 2D polygonalized rasterized images, right? If all the data that's going to these high-powered machines, which are capable of significantly more, are limited to 1 bit, right? We're losing control, right? And the idea here and the simple solution would be to just simply add color and grayscale to go much beyond where we're going. The second issue that is a recurring theme is compensation. Regardless of whether you're dealing with a powder bed fusion process or a sintering process, which requires, a green part, compensation is the name of the game. Hours and days are spent simulating it, and materials are qualified to go handle this. This basically reduces the freedom of parts that we can use and the freedom of the materials that we can use, and clearly the answer needs to be a generalized anisotropic compensation API. And finally, we're back to the ever-increasing march to how all machines are getting bigger, faster, more resolution, and the people who are using them are generating more and more complex parts. In short, the answer here is power. And to summarize it, the answer here is to use the engine that we've been developing to give back power, freedom, and control in all of these processes. I'm thrilled to announce the set of raster processes and announcements and APIs that we've developed. I believe that they're going to dramatically push the limits of what's already possible. They're certainly pushing them with already a number of key partners. You can imagine what we're probably trying to do with Czar to simply push the limits of what a printhead could even do. So let's dive in a little bit deeper into one of these topics, grayscale. So the idea here is when we have parts, we want to segment them and we want to apply advanced toolpathing. In a raster setting, advanced toolpathing can mean all sorts of things like dithering, anti-aliasing, etc. We're today going to be focusing on grayscale and beyond. The idea is to take a part and divide it up into all of its key segments, whether it be the core, the shell, whether it has a lattice structure, the outside, the inside, specific areas near the shell. The idea is that we can embed metadata into all these processes. But, to what end? So what you're seeing here is a high DPI image that has come out of the engine. And the idea is to take this data and dramatically improve the printing process, whether we're enabling functionally graded materials, whether we're creating an efficient way of generating challenging bid files, or handling metallic components and exposing different ways to make improved coils, heat exchangers, nuclear reactors, etc. The idea here is we can use this grayscale to fundamentally solve major physical and material graded problems. With this extra dimension that is now available in the toolpaths, the types of parts that people can make have significantly improved. Moreover, we suspect that a number of people will use this to improve the part quality and finish, because now you can have a graded grayscale on the edges. The next key thing that we'd like to talk about is anisotropic compensation. Right? It's clear that in order for mainstream adoption, we need tighter tolerances, and this needs to happen much faster. Right? We can't spend 10 to 15 hours compensating something just so we can print it and hope to God that the green part that comes out will come out the right way. And so to address this key fundamental issue, we decided that it made sense to create a number of geometric APIs for generalized anisotropic compensation. The idea being that if already right now, if you give the engine 6 scalar values, 3 for scaling in X, Y, and Z, and 3 for offsetting or compensating in X, Y, and Z, you're now able to fundamentally attack some of these hard and difficult problems quicker, better, and faster. You're using the GPU to fully modify all of these images. And what does this mean? It means more materials, more part families, more printer companies and ISVs generating IP, and quite honestly, faster and quicker qualification. The idea here is we're trying to build the tools to fundamentally accelerate how quickly people can develop sophisticated strategies. It's our goal to essentially be the best mathematicians in the room and enable every single one of our partners to generate more and more IP to run their machines to the limit. So let's dig again a little bit deeper. So here we have a test geometry. It's basically a helical fluid channel. The idea was it has a bunch of thin walls, and it includes positive and negative features that will receive corrections on the order of the feature sizes. Of course, showing anisotropic compensation is difficult because we're talking about microns, not meters. And the idea here is we're specifically trying to show in this example how this anisotropic offsetting is being used in this raster process to calibrate the machine. So in this world, and you might have to squint a bit, you'll see that we have a number of slices, and you can see that there's a certain level of black, white, and gray in these existing slices. We've now conducted an anisotropic offset on these slices, 40 microns in X, 40 or 60 in Y, and 80 in Z. And now you can see 2 key fundamental differences. Number one, because we are doing an erosion, you're going to see more white on the right, right? So you're seeing those rings and those little blemishes kind of contract a bit. You're also going to see the fact that the angle of the darkness in the ring is also changing. This is because we are offsetting in Z as well, and because it's a helix, we're just traversing further and further up the helix. Again, the idea here is not that we have invented the best way to go and compensate parts. The idea here is we've been developing a generalized API so that more and more people can take a much more sophisticated approach to doing this. The next thing I'd like to touch upon is performance. And if I could be given the screen share, that would be helpful. So what we have on the screen right here is a bunch of heat sinks, right? I have no idea how well this is coming across in the Zoom from a frame rate standpoint, but we are at 30 to 60 frames per second, right? And this is kind of a funny looking part. And the idea here is we're going to just simply take this part and we're going to go slice it at 50 microns. Okay, and of course I will shut off the visualization so I can give the GPU as much memory as humanly possible. So let's hit apply. What you'll start to see here on the right is the GPU spinning up. You can see the CUDA cores are running at max capacity. And you're seeing this oscillatory motion, and basically the slice is coming in on powers of 2 over and over and over again. Right? You can see how fast this is happening. You can see specifically the oscillations between when something is being computed and when it's being transferred off the disk. Right? This will actually be merged enough so that it'll be even faster. But the idea is we're generating high resolution images for this heatsink, on the fly live during the Zoom meeting, and we're already done. Right? And this is simply because the GPU has dramatically parallelized this process. So I'll stop sharing my screen and go back to the slides. So why is this performance important? Well, a number of things, right? We're not doing performance for the sake of performance. We're doing performance for the sake of what it will engender and enable from a business process standpoint. Being able to slice significantly faster allows us to A, try and test and simulate quicker, allows us to hopefully B, keep up with the machine, and C, the performance is necessary because one of the key values of 3D printing is the fact that complexity is free. But we all know that that's actually a lie. Complexity is not free. It's limited by your compute and your software. And so how can we, Dyndrite, figure out new and clever ways to use the existing software and hardware and the new, for example, NVIDIA GPUs coming out to push the limits of what's possible? Can we truly flip the paradigm of the manufacturing hardware being, much better than the software? So let's see if we can advance the slide again. So we've been talking quite a bit about raster processes, and I'm sure there are a number of people in the room wondering what else, what else could we possibly be doing? There is actually one more thing that I'm actually pretty excited to announce. It's the concept of support-free printing that I think everyone has been seeing all over LinkedIn and social media and on the internet. The idea being that it's all about the toolpads and what's kind of important here. So I don't need to go through why support-free printing is important in a laser powder bed fusion process, but I think I can joke ironically about the key pillars of support-free printing. So the first pillar is a geometric query, right? Dyndrite is going to be providing APIs to enable sophisticated geometric queries. A number of folks are already familiar with upskin, downskin, and inskin, right, and applying specific parameters to those specific areas in a slice. But the idea is we want to offer a much, much broader set of geometric queries to enable something very clever. The clever stuff is more and more advanced toolpads and more recipes and IP. The idea here is, can we figure out a way to enable every machine vendor on the planet and every single customer end user on the planet to quickly iterate in an automated way to generate new toolpathing strategies, new geometric queries, and then codify that into IP and recipes that they can either sell, keep to themselves, or donate to the public domain. The idea here is we're developing IPs to enable this IP generation and development, and again, to provide the fastest mathematics engine on the planet. So what does this look like? So we just talked about geometric queries and segmentation, right? And basically the simplest way to show that is what one of our applications engineers, Dalen, cooked up. You're seeing here essentially a sample part. It has an outer ring, which is thick. It has an inner interface, and then it has a number of fins. As you can see, zoomed in, we've applied a number of different hatching and toolpathing parameters to each of these sections, right? And these were all done via a specific type of geometric query. So the idea here is we want to enable people to make lots and lots of recipes and enable faster parts and newer types of parts quickly, The other type of query that we're enabling is the distance-based one. As you can all tell, we have a pretty darn fast voxel system internally. And the idea is that if you wanted to detect fins or near surface features, you'd simply use actually our raster processes in our voxel engine to also enable these very fast and very sophisticated queries. So let's go generate zones with the distance field. So in summary, we're enabling grayscale to enable much more sophisticated toolpaths and raster-based processes for binder jetting, DLP, SLA, etc. We are enabling a broad-based general anisotropic compensation API to, again, help all the ISVs and printer companies in the space. We are, of course, upping the ante in performance yet again. I think I was seeing a number of benchmarks recently that showed another 1 to 3x improvement. And then finally, we want to do something similar in the vector space. And the first area that we're targeting are toolpaths to enable support-free printing. The idea here is to unlock the capacity of the machines, new materials, and new part families with speed. As mentioned, Dyndrite's mission is to fundamentally change how geometry is created, transformed, and transmitted on a computer. We've seen what's happened over the last 30 years, and I strongly suspect the next year and the next 30 years are going to dramatically change where additive, is going to go. It's going to go from a prototyping process to a production process. It's going to enable a metric ton of IP to be generated. And it's going to fundamentally change the way we decide to manufacture things and how supply chains operate on our planet. I want to take this opportunity to thank all the attendees, developers, and DDC members. I also want to take this opportunity to give a special thanks to all the folks at Dyndrite that made this happen. I genuinely think that you're going to have an awesome time over the next 2 days. Welcome to DDC 21. Enjoy the show. And with that, it's my distinct honor and pleasure to invite onto the virtual stage Sam O'Leary.
Hi, everybody, and thank you, Harshil. So if somebody told me when I was an engineering apprentice 20 years ago that today 3D metal printing would be driving manufacturing the way it is, I wouldn't have believed it. To be quite honest, I didn't even know it existed. These were the days when you poured molten metal into a mold made through a complex multi-step process involving dipping into a ceramic slurry before spending hours literally hammering the sand off the cast parts. This was back when some poor dude was spending his days inhaling dust, working with historic equipment and processes in a scene that you might imagine was from the 1800s. But I'm talking about this as if it's over. It's not. This is still a fair representation of much of the world's manufacturing today. But others are choosing something else, something mind-blowing that leads us here to an era where additive manufacturing is pushing industries to create what a few decades ago would have been thought impossible. And it's doing so at unprecedented rates, well surpassing the speed and design aspects of which traditional manufacturing methods can handle. On many people's journeys to work this morning, 3D metal printing was at play courtesy of some of our amazing customers. If you were traveling via an electric bus in Italy, it might have had a power line connector that was made by 3DNA. Maybe you arrived by train, and as you pulled into the station, the brake pad could have been built by Webtech. It's possible that the sneering knuckle was imagined by Hirschvogel if you took a cab today, or in a dream world, if life is going well, you jumped into your Porsche or Bugatti or even private business jet. All of these with parts produced on our equipment. Anything from your new hip to life-saving components used by firefighting teams, 3D printing has really become an essential part of our daily lives. And it's funny because despite all the scars on my hands from the mistakes I made as an apprentice engineer, using all of those old-fashioned machines, today myself and our industry face a different set of challenges to overcome. They are, how can we shift this very cool industry to a place where it uses its full potential to deliver customer success? This is the topic I will discuss today, and I thank you for joining me as we delve into it. To talk about achieving the true potential of additive manufacturing, Where we are right now, we have to go back to its humble beginnings. Sometimes I pick the brain of one of our chief engineers, Dieter Schwarzer, a living legend in the additive world and one of the original patent holders of this technology. When he explains what it was like back then, it's crazy to think of how far we've already come. 25 years ago, build envelopes of these systems were tiny, roughly 15 liters in volume. Today, our build envelopes have increased dramatically and can hold a whopping 216 liters. To put this into perspective, let's use the example of something built on one of these machines, the size of a matchbox. If this was done 25 years ago, the matchbox may have taken 24 hours to create. Today, would be created in just a few minutes. The cost of the matchbox, well, to build it back then may have cost between 500 and 1,000 euros. Today, maybe 10 euros. And also, unlike that bygone era, metal 3D printers can be unattended as they pump out production components day after day, week after week. This would have been impossible a couple of decades ago. As you can imagine, this view on additive manufacturing from one of the pioneers of the technology is thrilling. And although it's clear we've already come so far, let's be honest here. There are still significant barriers to overcome for our industry. Despite many people in the industry claiming otherwise, you have to realize that if somebody tells you what is done here in this industry is easy, walk the other way. So thinking of the barriers, the build plate sizes are restricted, the part economics are hard to grasp, the materials are limited, the pre-processing software is a pain in the arse, the post-processing can be difficult. However, in the past years, we have worked tremendously to engineer solutions for these problems, and the results of this work start to become clear. Today, despite obstacles remaining, industries ranging from space and automotive to energy and health realize that the promising world of additive is a solid and future way forward to implement their out-of-the-world ideas while accelerating their visions into reality. Another roadblock is the additive industry itself. Yes, us. Why? Because you will always know your business better than we will. You are the experts. And our current problem in it is we have AM companies that try to create full manufacturing process solutions or a fully integrated factory solution for their customers. Let's get real. We can't go to BMW or Ford and tell them how to automate their production. This doesn't make sense. So when we look at the issues I just talked about, what can we do to solve them? Firstly, we must admit that the current situation is not perfect. The world is not some shiny bullshit Instagram account that we see every day. Nobody has it all fixed. We have to be open and honest about this. During today's talk, I want to talk about some of the companies and key industries that we have successfully enabled to arrive at volume production. Would they look back at the last few years and say, hell, this has been perfect. SLM Solutions has been perfect. Their partners have been perfect. Their machine performance has been perfect. Their build preparation software has been perfect. Of course not. At some point, there has to be some acknowledgement that there's a great deal of work to do to get us where we need to be, to get our customers where they need to be, and essentially bringing our customers to a place where they hit epic sweet spots is why we continue to develop today and tomorrow. But first, we must be honest and acknowledge that we can't do it all. What we can do is illustrate that we are trying relentlessly to understand our customers, that every day we are trying to meet our customers' needs in new and unprecedented ways. This is the only way we can get close to ensuring long-lasting customer success. Lately, additive's got a bit of a rock and roll reputation. Soon there'll be a 3D printer on Mars, things like this. But I want to start here on Earth because there is no way that we will affect outer space without first affecting planet Earth in a cool way. So what's happening on Earth? Well, there are millions of people doing extraordinary things, while billions of us need exceptional solutions to the mechanics of daily business. One way additive manufacturing is impacting people's lives is by helping to save them. Take ExOne. In a joint innovation project, we designed and produced an AM firefighter pump with a 70% reduction in weight and increased resistance to seawater corrosion. The lead time was reduced from 20 to only 4 weeks, lowering inventory capital and costs. And if we look at an automotive case, we have to bring up Bugatti and their brake caliper. Volumetrically, this part is the largest functioning titanium component built with selective laser melting. It can cope with extreme strength, stiffness, and temperature requirements. Caliper tests showed a tensile strength of 1,250 newtons per millimeter squared, and also a material density of over 99.7%. We also worked with them to create a heat shield installed in all vehicles since delivery of the first Bugatti Chiron from the production facility in Molsheim. It's also worth mentioning that our proof of concept with Porsche using the SLM Solutions NXG12-600, where we successfully printed a complete eDrive housing with innovative AM design, all the advantages of AM have been implemented in this housing, such as topology optimization with lattice structures to reduce weight, functional integration of cooling channels, higher stiffness, and reduced assembly time by the integration of parts, as well as improvements in part quality. To something a bit more related to normal life. In the transport sector, we have worked with 3DNA using reverse engineering to 3D print trolley heads that connect each bus to the network's aerial power supply lines and mechanically guide rods to the bus's roofs. Today, there are no trolley heads left that have not adopted AM technology cruising around the beautiful city of Naples. And if we take to the skies, our joint project with Safran Landing Systems, where we've successfully implemented our technology to produce a component of a nose of a landing gear for a business jet, a world first for a part of this design redesigned for metal-based additive manufacturing, additive guaranteed time savings, and a huge 15% weight reduction. From those stories, we are getting solid indications of what we can do for our customers. We see it every day. We see it in the factories of our many customers who operate production fleets. And we see it by looking at the output of those fleets. But we always want to go further and ensure customer success in more ways than the machine themselves. We want to replicate the success of some of our most mature customers and democratize that. This brings us to talking about an additive manufacturing future that is almost at our doorstep. A future where it is more automated than ever before, and it's not a highly skilled process today. Yeah, of course, this is a dream world where everyone gets their kicks thinking about it. It's like both engineers and OEMs want the same. It's not even far away because many of the goals we set for the future, we are already implementing in our current processes. I'm talking about a future of AM where customers don't just have machines, but have an entire ecosystem integrated into day-to-day operations. And how will we continue doing this in the future is by a course of action that extends much further than the mere purchase of a system into an overarching living solution where your systems grow with capabilities and as you grow and develop your visions. And how do we do this? We make it open. In fact, for the future of AM to come to its tremendous potential, it has to be this way. How do we unfold the future using open architecture to get closer to a push and play reality? Firstly, we get there by applying our 25 years of experience and knowledge in everything we do. And again, not just doing this alone, us providing interfaces to the likes of Dyndrite and many others, all of whom can enable more of what our machines can do. Yesterday, I spoke to a customer. It was thrilling. She said, I know how to get more out of your machines than you do. And this is a compelling and motivating statement to hear. And this is because you realize that sharing knowledge enables our customers to do more and allows them to move forward. And in return, it allows us to enable and improve our systems, improve the software, improve the interfaces, and in the end, improve the output and the industry. So if you're an AM company saying, I am the machine manufacturer, I am the forefront of all knowledge, I don't allow anybody to change things. I know best. I don't allow engineers to play. This is a big problem. This is a big problem because you'll never know more than your customer in how best to produce a turbine vane or how best to produce a brake pad for a train. The people who have designed these for years and know the operational conditions, they know how to do that. So when I think about how additive can reach its potential, I believe that we all need to stand up and be brave and say, hey, okay, let's share our knowledge. Let's work together. Let's get to that place. It's a mutual respect and understanding that will allow us to develop the technology, to continue to develop, and to reach uncharted territories. So this is it. Everybody has to give their input to make it work. And the way we achieve that is by working together, exploiting everybody's knowledge base, exploiting everybody's strengths, and to deliver the ultimate solutions for all of our customers. And yes, in some respects, this is already happening, but in many ways, it still has a way to go. Why? Well, because it's incredibly complicated. There are a million different things to consider. Of course, it's been slowly developing year after year with multiple partners, with software partners, with hardware partners, with automation, working with the FAA, working with a complete broad spectrum of people, powder suppliers, everything needed to make it happen. But there will never be one company that can stand there and say, hey, we did it alone. We enabled Additive to reach its potential. It will only happen with companies working together, focusing on the added value that they can have to each part of this very complicated ecosystem. What we can say is this: we're open for business. Let's enable each other. Let's do what it takes. And when I say this, I'm talking about working with partners from the full value chain, because it's what our customers want. It's what the industry needs. By accepting powder from whoever the customer wants to choose, by allowing customized service solutions, by allowing interfaces to all kinds of different software, whether it's build preparation, whether it's ERP system interfaces, this is the flexibility that's needed to move forward. The importance of open architecture is that we are experts in what we do. The customers are experts in what they do, and it is the perfect solution to meet halfway and allow each other to deliver their expertise. These partnerships are much more fruitful than a closed system. For example, in dental implants can never be designed and produced specifically to the patient's anatomy. They enable a more efficient surgical procedure, achieving a functional and cosmetic restoration. The production of patient-matched and custom CMF implants by selective laser melting is more efficient and economical than traditional CNC milling techniques. In medical, patient-specific hip cups made on the SLM 280 are made with a build time of around 30 minutes per part. Here, our customers can achieve the fine details needed across the porous geometry for optimal connection between the implant and the bone to encourage long-term stability of the implant. On top of this, the machine enables the user to control the design of the tunable lattice structure. Traditional plasma spray coating of this processes cannot match this level of control. In automotive, take the example of Divergent 3D. They have a complete production system, an adaptive production system. It's a software and hardware solution designed to replace traditional vehicle manufacturing. They implement our additive manufacturing technology to create an automated manufacturing cell that allows automobiles printed with not just one or two 3D printed components, but several hundred. They can engineer, 3D print, and assemble vehicles while seamlessly moving manufacturing between different models at will. This drastically reduces cost, making the production of vehicles in small batches a profitable reality. In space, SLM Solutions collaborated with Cellcore to create a monolithic thrust chamber, a rocket component that not only has to have a consequent lightweight construction, but must also be able to withstand the exceptionally high stresses. Additionally, the manufacturing costs for their complex geometries are very high when compared to conventional manufacturing processes. In this case, our customer success team developed specific parameters for the geometry to satisfy the aerospace industry's high material requirements, and the engine was manufactured in the nickel-based superalloy Inconel 718 on our SLM 280 equipment. Each industry is unique, and we make sure we can cater for every one of them by customizing our machines for their exact needs, whether it's dental, whether it's space, whether it's using aluminium, whether it's using titanium, whether it's a company like 3DNA, whether it's Bugatti. We're working and we're going to enable as many build visions as possible. Customers will always be reliant on good quality powders, good quality build preparation software, good quality open interfaces to pieces of hardware that run a reliable industrialized software base and hardware base. They're reliant on proper quality assurance methodologies, whether it's in-machine melt pool monitoring or CT scanning afterwards. It's then a matter of industrialization into a factory setting. This could be how us, as a machine manufacturer, provides open connections so that people can connect it to a factory management system. They can visualize factory planning. This is how you enable automation at scale. So how do we create a course for action? Of course, in some ways, we are on course, but the way we wholly achieve it is not by one company or by one piece of technology. Instead, it's a broad ecosystem that leans on the applications of multiple complementary technologies, leading back to the idea of working together by bringing our expertise and your expertise to the table to find solutions. This means partnering up. In turn, this will enable our fundamental goals of doing what it takes to realize the future of delivering what our customers and what the industry needs. Essentially, giving the toolkit to be successful and disrupt your industry as you grow. So what does it mean to disrupt the industry? Well, to start, it's the disruption of traditional supply chains. It's the shaking up of conventional business models. It's the ability to produce 1,000 vehicles instead of 100,000 vehicles and still be within your financial goals. It's the moment in time when you can create just one part, courtesy of AM technology, before moving on to your next brilliant idea. This kind of disruption advances the pace of technologies and advances all of the improvements that we see in the operation of a piece of equipment. Kevin Zinger, CEO of Divergent, said this: technology agnostic, looking at all the current technologies and combining them into new production systems, where AM is one component, the key driver being software, taking a design, running it through all necessary engineering simulation, and then printing that design, meaning you only put material where it's needed, resulting in a lighter, stronger, and durable application than any existing manufacturing technique. I couldn't agree more. And it's incredible that despite the leaps and bounds our industry has made, there are still people in disbelief that AM is not and will not become a mainstream solution. Really? As of right now, SLM solution machines have millions of operational hours of 3D metal printing to create millions of components for some of the most innovative companies in the world. This is on around 700 machines scattered around the globe. Every day this number is growing, and with it the mindset, and the right mindset, that these solutions are just the tip of the iceberg. But what about its potential? Our view is that to achieve it, we all need to be aggressive, and we need to make incremental improvements to this process and to the technology. But I see it differently. The way we get to the true potential of AM is by being experimental, by being flexible, and by being open. We need to come together, share our knowledge, put everything on the table, and use these elements to meet our customers and to satisfy their needs. Anybody can put out a view of what AM is going to be, but there could also be vital technology breakthroughs within our technology field that will change the direction a little bit. Kind of like what we did last year with the NXG12-600 when we released it. But to do that, and to disrupt, and to learn, and to grow, and to shake the sector even more wide open, we have to keep making cool stuff. Keep working with the best people, keep listening to our customers, who know more than we will ever do. And mostly, we need to admit that we don't now, and we never will know everything to succeed. And then, if it's done, what might I say the future of additive looks like? Well, then our journeys to work might be even cooler. They might be filled with cooler additive technology in different types of vehicles. The bus or the train you travel on might even not be a bus or a train. The office you sit in, everything around you, to the Wi-Fi, transmitting satellites, all built with additive. The list goes on and on forever. And in space, we can't forget space, of course. What we build to get there and what we build when we are there will be enabled with the help of additive. So if you're planning on going to Mars and want to make your life a little bit easier for that, get in touch with us about the NXG12-600. So from me, that's what it takes to achieve the true potential of additive and what a team we have with us on our journey to get there. We have the world's best engineers on board, and we're constantly looking for more to join us. We have a permanently open set of positions for those who want to work on cool shit that drives the future. We have a bright day ahead of us in AM. The days of poor engineers working on crappy belt-driven polishing units, inhaling dust all day, they're on the way out, and we can look forward to a new future together with our partners and the people that want to make this happen. A future that is not bound by outdated assembly lines, ridiculous lead times to manufacture a product, absurdly huge production volumes to make things financially feasible, but a future where we are free and are only bound by the limits of our imagination and what we want to design and create. And the most exciting part, it's here right now. That's it from me here in Lübeck, Germany. Thank you for everybody for the time. And most importantly, thank you to Harshil and Dyndrite. It's our pleasure to be involved in your journey. Thank you.
Hi, Sam. By the way, that was an awesome talk. So I'm seeing a couple questions here, and again, I'll say to the attendees, you're all more than welcome to ask more. We are real people reading them, so we'll try to get through some of them. But I'll just ask them. There's 3 here, and we'll hopefully that'll lead to a discussion. So Sam, the first question is, where do you see the automation boundary between suppliers and SLM solutions? What kind of interface is needed to embed an essentially batch style 3D printer into a continuous manufacturing production line?
It's a great question. I mean, the lines are clearly blurred. There is automation to make sure the machines can operate. You can reload a new job. What I talk about, not telling BMW or Ford how to automate a production line is obvious, right? These guys have been doing it for decades. They know better than we do. It is, in my opinion, our job as a machine manufacturer to automate what we can control. So automate the restarting of build jobs. But as you take things away from the machine, as things go to further downstream processes or upstream processes, this is, in my experience, best dealt with by our customers because it's different. Everybody's got a different view on this. And kind of having the arrogance to say that one size fits all for an automotive manufacturer or for an aerospace manufacturer, quite frankly, I think is arrogance and a little bit of stupidity as well.
I agree with you. I mean, it's honestly very akin to kind of our approach too, right? I mean, it's not our place or our goal to tell people how to run their machines, how to run their business, tell them what their business model is, or tell them what their unit economics should be, right? Our goal is, to be tool makers and to be humble and to provide tools so that they can come up with new and interesting things that, we didn't even think of, right? So I agree. It's going to definitely require a different approach for this to happen, and it's not going to be blanket across every industry or even every customer. So next question, and I guess this is a bit of a leading one, but I promise I didn't plant it. You've told us that you want to give more freedom to your customers, also in the choice of materials and their source. Do you also plan to introduce software that helps your customers develop new custom printing parameters for these materials?
This is an interesting question, of course, and of course that is our intended path forward. I mean, I tried to touch on it as much as possible. Anything from, I can tell you so many discussions I have with our customers that are really successful in printing large scale applications. The thing that's always clear is, we take your technology, we work with other pieces of software, we work with everything that we need to make this happen, and do not have this belief that you know best how to do this. Of course, we know what we do well, and we do that well, and we know what companies like Dyndrite do well, and how they can and how you can, Harshil, impact what our customer experience is. And that is kind of exactly what I wanted to get across today, that we want to be as open as possible, because I truly believe that's the way we move forward, and that's the way we really open up the success that we've seen in a lot of applications already to a much broader spectrum of people by essentially removing the limits. I think, Harshil, you mentioned it earlier, we've developed a system, and one of the concerns that I've got is that I can print faster than the data can be prepared. In what world is this a reality that the speed of the hardware process can exceed the speed of the software process? This is a situation that, of course, needs to be solved, and I think we
well, it's ridiculous, right? It's fucking ridiculous.
Nobody can believe it's a real problem, and I think you hit the nail on your head in your opening remarks. It's bullshit that can even be a discussion in 2021, right? This is this is not how the world should be.
So, I mean, again, then to kind of follow up on that, right? In this, I mean, it's clear that you and SLM, I know SLM has been fairly open since the beginning, right? But it seems like you guys are really pushing the envelope on what that means and how this is going to, hopefully lead and dramatically change the industry. I guess the follow-up question here is, what about IP? Like, are you worried about that? Are you thinking about that? Are you taking steps to go manage that? Because to be honest, that's been the catch-22 situation for the last 3 decades. Everyone is so afraid of IP that, I think things have been at a standstill. How are you overcoming that hurdle?
I mean, it's a fair concern and a fair comment. Of course, everybody has got elements of the process that they want to protect. And of course, that is where core IP is held. And we're no different to anybody else in that regard. The way I look at it is there are certain kind of core process knowledge that we need to keep internally, which of course we can, and we can put restrictions on kind of how that's accessed and how we work together with companies to get through that. It's not as if there isn't IP issues here. Of course, there is significant IP issues. Us, like everybody else, has got to find the right combination of the way to work around that. So to be open to an extent that it makes sense for our partners, and to be open to an extent that kind of doesn't give away our crown jewels as well, because we've got a business to run. We need to be successful, and me saying, hey, welcome, come and see everything that we've got is not exactly a great business strategy. And that's not what I'm saying. It's managing this in a way that gives the potential added value to our customers through working with partners, and also protects the kind of core know-how that us, like others, have developed over now decades of development of this process and technology.
I mean, that almost seems too logical and sane. Right, like you're making too much sense, too much common sense, right? So I guess the follow-up question, there are a couple here. It's, how, will we see a move forward towards open material platforms? And a second kind of tag on is, what does support-free printing mean to you?
Well, I'll address the second part. I think, Harshil, you mentioned some LinkedIn activity. I have no idea what you're talking about with support-free LinkedIn activity. We've been playing a few games recently. No, with support-free printing is it's a cool topic, and I'm not going to answer that question because we'll be doing some further communication about what it means to us and how that is enabled. But again, this is not a single answer topic. This is a multi-answer topic that involves lots of people, lots of different knowledge sources, in the end to create something that helps the customer base, customers of yours, customers of ours, joint customers, everybody in additive manufacturing, to really drive this forward. I don't want to see any more charts that don't become reality. We all know the potential of additive manufacturing. I see it day on day, as do most of the people on the call. Now's the time to really make it happen, and it's making it happen by working together. Harshil, the first part of the question was what? Sorry,
when will we start to see more open material platforms, and can you elaborate more about the material side of things?
Yeah, I mean, this is a great point. I mean, we're personally putting a real emphasis not just on the existing materials, but also new materials as well, working with new partners to look at the alloys that we have, improving the alloys, but also looking at different alloys as well. I saw some interesting metrics in terms of nickel-based alloys. The Inconel 718 is accounting for Christ knows what percentage of applications. Yeah. There's a reason for that, because it's the easiest one to process, but it doesn't mean that is the kind of end state. If you look at superalloy development over the years, superalloys were developed for a specific purpose. We're not really in a situation where there is a whole world of alloys that were developed knowing that additive manufacturing exists. This is a real fertile ground, and extending on that in kind of manipulation of the process parameters to really fine-tune parameters in specific areas is a huge area of focus for us, and watch out for some further announcements in the coming months in that regard too.
So another kind of follow-up question is, I mean, additive is sort of all about its applications, right? Like I think I'd see, whether it be software companies, materials, like as you just mentioned, or hardware companies, they're all trying to find that one niche kind of key special use case, right? And of course, you guys have found impressive and important use case for decades, right? I mean, you mentioned a number of them even in your talk, right? But if you were to kind of concentrate on one key area, or maybe kind of an abstraction, what ties those use cases together, and what direction should people, the users of your machine, be looking, right? Like to find these special use cases.
You know what always breaks my heart, Harshil, is when we see application cases that come in that is just a part that was designed for traditional manufacturing. You say, hey, you've now got a machine that is fast enough to print this in a way that is economically viable. It can be cheaper than the traditional method. Okay, cool, but that's not the point, right? The point is you've got to exploit the technology and deliver. And those are the application cases that are really cool, where people have understood the limits of the technology, applied all of this knowledge to create something that is cooler. Yes, there is a cool situation now. We can manufacture stuff at a level of productivity that, to be honest, nobody in this industry thought was ever going to be possible. It is possible, and it's going to continue to be improved on. What we've got to do is make sure that these application cases where things are properly optimized for additive manufacturing are known and are kind of shared, and give our customers the capability to develop this. And this is, in a way where we don't need the world's best application engineers to develop that, where there is software solutions and understanding for people just to go ahead and do that. The cool thing that I would say is, traditionally, everybody looks at these cool application cases and say, hey, yeah, space applications, aerospace fuel nozzles, blah, blah, blah. We've seen it all for years. What is happening now is that there's more day-to-day applications. Look at the bus story. This is simple stuff that a few years ago you would have never associated with additive manufacturing. In day-to-day mass transportation, there is more and more use cases. And I jokingly use the Bugatti example. Yeah, the Bugatti example is cool. It's where the technology was years ago in terms of kind of economics. Now you can translate that to any day-to-day vehicle, and that is really the cool thing, and that is the most important thing as to what's been opened up with advances in technology on the hardware, and of course moving forward with the software as well.
So I think the thing that I'm really resonated with what you just said was this whole, you don't need the world's best application engineer to go do something, right? I mean, I also have the sense that, you need an entire room of PhDs to figure out how to design the part, then figure out a way to transform the part into some kind of additive CAM, then figure out how to post-process the part, and then, basically run the machine, right? And it seems like, you kind of agree that one of the other key issues that need to be solved is one of, democratization, right? And democratization is not just about making cheaper machines. I mean, quite honestly, I don't understand why machines are getting cheaper. They should get more expensive as the parts get and things get more valuable and more interesting, right? But it becomes a democratization on how to run the machines, how to learn the software, how to learn about the process. Is SLM doing anything in the democratization or the education space at the moment?
We are, and we don't scream and shout about this, that this is what we do kind of day to day with our customers. It's kind of part of the service that we offer in developing that exact structure. You said it yourself. People don't need or don't want groups of PhDs to operate a machine or to run application development. For one, kind of having that interface creates problems in as much as you're reliant on a human to understand what's important, where support should be. This is not how it would be. This is, how we work with our customers, how we intend to continue working with our customers to be able to deliver these solutions and to be able to deliver this kind of consistent and easy approach.
So I think we're slowly starting to kind of wrap up on the questions. Sam, did you have any other kind of key last thoughts, or maybe what's a question you wished you were asked that you had the answer to answer, opportunity to answer?
No, I think most of the key stuff has been covered. I do want to dwell on this point. Don't underestimate how important it is that there is a kind of acceleration in the full process chain of what's needed. You alluded to it, Harshil, that there is And there cannot be no situation in the world where software is behind the hardware. And this is a legacy situation, a situation that's got to be solved, and a situation that I think is solvable working together, understanding the needs. And in the end, I want to enable people to really get the benefits of the technology that we've developed. I know that there is more capabilities from our existing machines and more capabilities from our NXG machine that can be opened up with this type of approach. And that is what we want. It's how we will be successful. And it's, of course, how other companies in the ecosystem will be successful as well.
I agree. I mean, to be honest, I think there are too many problems and things to solve and figure out, right? And to that end, there's no point in being greedy, right? And that, I mean, I always kind of laugh when I see a number of the printer companies say they're, quote, full stack companies. Saying I think that saying is a mental illness brought on by Silicon Valley, right? I mean, there are companies that are good at geometry. There are multiple multi-billion-dollar companies good at simulation and a variety of processes. There are a number of companies that are good at materials. They're good at ERP. There's, like you said, there's a whole ecosystem, and there's plenty of problems for everyone to solve without everyone trying to play grab on what they have, right? So I agree with you all across the board. So I'd say thank you, Sam, for your time today. I appreciated your time with the keynote and the question and answer session. I think I've gotten through the majority of the Q&A questions, so a bravo to all the attendees.
Welcome back. The program will now resume. Please welcome CEO Essentium, Blake Teipel.
Hey, good morning, good afternoon, everybody. Great to be with you guys. Pleasure to have a chance to address this community. We're excited to join the community. So to our Dyndrite colleagues and our new colleagues in other spaces, we're excited to be joining the community. And so I'm excited about the future of software that we see represented here, and we think it's a very powerful vision. We're excited to be a part. So let me go ahead and share my screen and get into some slides. Try to keep my slides light and fun and ideally as well somewhat informative. So the whole kind of point today is thinking about additive from a dual use lens. So I'm going to introduce Essentium to those of you who may not have seen us for like a while, and a lot of the industry has been sort of on hiatus because the COVID pandemic has really prevented sort of the in-person information exchange. We're delighted to be able to jump online and do an information exchange, obviously today, and again, have a conversation really on a virtual stage. So again, the title of my talk today is short talk, just additive 2.0 through a dual use lens. There's a lot of discussion right now about sort of additive 2.0. Is it hype? Is it buzz? What is this whole thing? I think there's something to it. I think in essence, following on, and by the way, Sam, great talk, tough to follow after sort of that great talk. I'll do certainly my best, but in essence, as we certainly are, kind of racing to the factory and moving into production and moving into a sort of future state where additive is a go-to technology for production, then that creates context where we learn that government users and industrial users are sort of all facing similar challenges. And so that's really, in a nutshell, kind of what I wanted to talk about today. What are the challenges facing, folks on the governmental side, in the industrial side? How are they basically the same challenges, and what can be done about that through a digitally enabled future? First, just want to have a high level sort of Essentium at a glance. We launched in 2013 as a materials research company. Some of you may recall we launched in 2015 in the additive space with a technology now called Flash Fuse, where we use plasma welding inside of a printer to make parts that are isotropic in the Z direction. And also, we use a multi-layered filament architecture where we take thin film technology and sort of wrap it around the filament. And so there are a variety of value propositions there, harkening back to thin films. My own background, I got my PhD in material science. And so I'm sort of the materials person, and my understanding of software is very limited, which is one of the reasons why, certainly being now a part also of this community is something that I'm really looking forward to just learning a lot and growing in our space. But we've got around 130 employees and, global presence. So stop on over to Essentium.com, check us out if you haven't done that. recently. So when you think about the scaling challenges for manufacturers, right? Sort of what are the challenges that manufacturers, and again, government clients, but certainly manufacturers, what are they facing? Well, they're facing rising costs, challenges from a production timing perspective, and a skills and technology gap, right? Again, couldn't agree more with one of the major points in the prior talk, where really you shouldn't need a PhD at all in order to be successful in additive, whether that's on the part design side, whether that's on the material selection, or whether that's on the usage of the machine, bringing all those together, to provide a solution at the end of the day that your clients can win with, right? And again, we're here all together to help our clients win more, because as the world prints more, the world is generally, our thesis is, a better place. Because supply chain challenges have never been more acute, right? Whether it's a trade war, a pandemic, the Suez Canal getting blocked, or force majeure events due to weather, these are all of the gremlins that sort of jump up and disrupt supply chains. And suffice it to say, at the end of the day, disruptions are ever the new norm. There has been a loss of talent as jobs and technologies and manufacturing techniques have been outsourced. There has been a attempt to sort of reshore or onsource in sort of high skilled, and high cost regions, to bring some of the jobs back or bring some of the technology, the techniques back. But that has just still been limited. There's been a limited access to true scale. And again, we should be careful not to bound scale purely numerically in terms of number of parts or number of widgets or number of solutions per year. If you're in aerospace, you may make 10 to 20 units a year, and that's full scale. If you're working on a solution for a phone, you make 10 to 12 million units per quarter, and that's scale. But scale comes together in an additive context when you have the digital thread, you have a solution to track the digital twin of the part from CAD all the way through the production of the printing, into the post-processing, and out into inspection and into the rest of the world, where you can actually start to have ideally regionally distributed production, not just regionally distributed parts and components, but select production solutions where you have, again, a regional footprint that's designed to bring about those solutions where production and consumption are more and more co-located. So as you think about these challenges, again, that we're facing with our clients, with our customers, and additive is a great solution to pretty much all these challenges. And the manufacturing imperatives have never been more urgent, whether it's inventory reduction and supply chains, all the way through down to the transition to the digital factory. You think about that factory future is and will be digital in the future state, right? This facilitates mass customization. It facilitates a reduction of tooling. It facilitates these solutions where you can make cars, as was highlighted in the prior talk, where you're bringing together additively manufactured parts, subtractively manufactured parts using automation, and you're doing so in a more custom scheme that sort of unlocks customer choice and a reduction in lead times and all of these other value propositions of which many of us are so familiar. Because folks, if we think about sort of this, again, where the industry is right now, there is an advancement in supporting technologies. One of the things I love about joining this community is because we're looking at advancements in access to data through better use of computing horsepower, access to better simulation, and all of these sort of various facets. So is it hypey, is it buzzy to sort of say that Industry 4.0 is within reach? I really don't think so. I think that we're right on the cusp of all these adjacencies coming together through what the folks at HP are doing, through what the folks here at Dyndrite are doing, elsewhere in the community writ large. We're seeing this future state where Industry 4.0 is sort of right on the cusp. Okay, so having said all that, I actually now sort of get into actually the topic of the day, which is, again, Additive 2.0 and the dual use lens, right? What is this dual use lens that people talk about? So forgive the next slide. It's a little bit, if the previous, discussion was in bold strokes, this is very, 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 very crisp. So you sort of have these use cases, right? And so very hierarchical, very detailed. All of a sudden, we're getting right into the weeds. So we've got tooling and jigs and fixtures and masking and automotive, oil and gas and aerospace sectors, just to name a few, right? And so here are some of the use cases where we can bring about this factory level change, this manufacturing process flow level change. Well, these are the use cases that you see in commercial AM, commercial additive manufacturing. Well, the good news is that they're actually the exact same use cases that the governmental users are facing. Whether you have to service an aging vehicle, if that's an airplane or a car or, some sort of transport solution, nearly all of our sort of transportation that the government uses at the end of the day is actually pretty old. If you look at the serial numbers, if you look at the generations, the F-22 was the first, military aircraft designed solely in CAD, right? So everything else has this very old architecture. And so you have to service it. You have to sort of support the sustainment of the solution at scale. And so you need a low-cost, distributed digital lens in order to make that solution come about at scale. So what does that look like if you're sort of in the government space? Well, they have a cloud solution that they need to bring about where you have distributed, network architectures, you have distributed manufacturing solutions in the form certainly of, Essentium's HSE printers and other solutions, but you basically connect to the cloud. You have all the metadata, you have the technology data packages, and there are technology data packages that have to be designed for airworthy parts in this case, or they're designed for ground support parts. So components that touch airplanes but don't fly, and then components that fly on airplanes. Well, all of that has metadata. It all has QMS and COA and specs and all this information that has to be created, curated, checked, protected in a trustless environment. And then that information has to make its way to the machine. And ideally, the use case is simple enough to bring to life that somebody does not need a PhD or high-level training to make this happen. Because the folks that are keeping, the government moving, whether it's our government, governments for allies, et cetera, these folks are busy. They've got a variety of job codes that usually don't necessitate or facilitate super advanced training in one functional specialty. They have to be generalists bringing these solutions to life. So how do you do that? You have to have distributed design, distributed resources, hive production, and all of that boils down into centers of excellence as well as we start to see these solutions rolling out. So certainly we've got an example of that at Essentium. Again, I certainly invite you guys to come down and see us at Austin, Texas at our headquarters. We've got a basically example here, first use case of a hive and center of excellence based model that we're building parts, building solutions, building use cases, and rolling this out across the government. What does that look like? Let me give you some specific examples, some use case examples that come from the lens of a dual use environment. So the first step is just exactly the same, whether you're focusing with a government client as it is, whether you're focusing with a commercial client. You have to define the customer requirements for, you guessed it, the material. What is the material requirement that you need at the end of the day? I couldn't agree more with the previous speaker when there was a discussion, Sam was mentioning, we have to bring about a future state where that is open, whether it's powders or filaments, as is in Essentium's case. We have to bring about a state where the customer has choice. The customer has the solution to define what their usage environment is. And then additive manufacturing companies need to work with those clients at scale to say, okay, how do we pick a polymer or a composite from the pyramid here that fits the requirements for chemical resistance, functional properties, thermal, mechanical, and the rest. I'm happy to say there are a lot of solutions here. The costs are coming down, the access is improving. And if additive manufacturing becomes truly relevant to Industry 4.0, the entire ecosystem must resemble the ecosystem that we see at scale in conventional factories, in actual manufacturing. And so you can see there are general applications in the industrial space with molds for light bulbs or other items that need blister pack solutions, water bottles for a blow molding application, shaft inspection jigs, cable management clips, impellers, printed circuit board trays that are electrostatically dissipative and clean room safe. If you print these parts and you've got an open architecture and a cost-effective solution, then you can save your client time and money at scale in a material way. And this is what we need to see in order to have folks change their behavior, adopt a new technology, and for Industry 4.0 to come as additive manufacturing becomes unleashed. Because additive manufacturing, make no mistake, it has been stunted. The industry has been slow to grow. So let's look in the aerospace sector, both governmental and private. In the case of these red parts, this is a TPU anti-stat material that is used for protecting satellites from foreign object and debris. These are covers that are placed on satellites and they're removed prior to launch. Literally, it's 3D printed sort of in the bottom of the cover, remove prior to launch. And then you have assembly jigs, again, to put satellite arrays together prior to launch. On the right-hand side, you can see actually aluminum replacements, and we're starting to see in cases where you need to service a very old airplane and wing skins may be delaminating from phenolic resins and honeycomb structures that were put in place in the 60s. Instead of machining the part out of aluminum, we can print now, and having conducted sort of adhesion tests to confirm that a polyether ketone-based chemistry will adhere using drop-in adhesives to the aluminum skin and the aluminum structure above it and below it. We're starting to see massive solution opportunities again at scale. And so these solutions save on average more than 95% cost and time. So friends, this is a great moment in the additive industry. It's a great moment to celebrate together the victories that we can all cling to, because it's not just about one company or one technology. It's about the ecosystem, us building together a future state where a rising tide lifts all boats. Here's some more examples. So we had ground tooling. This is all government examples. And so we had FOD covers printed from carbon fiber materials. We had FOD covers printed from TPUs, radio trays, simple stuff to keep very, very expensive, as it turns out, radio equipment from falling, breaking, and being difficult to transport. Very large parts at times, leveling fixtures. This is a 6.4 kilogram part, 19.7 inch or 500 millimeter in diameter, printed in about 36 hours. You also have drip pans to keep solvents and avgas and hydraulic fluid from sort of spilling and causing health and safety problems. Back on the commercial side, we had examples where there were major bottlenecks in conformal coatings for printed circuit boards. So by printing, masking technologies for PCB and PCBA solutions using electrostatically dissipative safe materials, we were able to help our clients cut their costs by more than 90%. These are the solutions that are needed, solutions like this at scale, to help improve access to new technology and new lead time cuts. On average, there's over a 77% increase in efficiency, and we're cutting the labor time significantly. Also with another client in the high spec automotive and motorsport case, Kozlowski Advanced Manufacturing. But it's not just Essentium, and it's not just SLM, and it's not just the parties here today as part of the Dyndrite community. Additive manufacturing is anticipated by an MIT study that was recently published, over 90% cost reduction over traditional manufacturing. So again, friends, this is a great moment. It's a great time. But what, again, is another future idea, another future example of how we stay moving ahead of the curve. 2021 and beyond, how do we stay ahead of the curve? Well, design for additive is one of the next frontiers. So I grabbed some images from the Wohlers report, and I just sort of said, okay, how do we again communicate this true opportunity for part consolidation, lightweighting, better design freedoms, and these other improvements? As you sort of move into this future state where, again, the knowledge base is accessible, the knowledge base is transferable, the materials are open, the machines are fast, we start to see design choices being made to minimize supports in this case, improve print orientation, and increase throughput. Also for conformal cooling that creates, again, better parts using additive than could otherwise have been created using subtractive. So we need to ask ourselves, right? How can we help prepare for Industry 4.0 now? How can we help our clients prepare for that? So as I wind down my talk and save a few minutes here for Q&A, I want to say a big thanks to Dyndrite. Thanks for putting together the community. Thanks for putting together the developer conference. We're delighted to join the community. So a big thank you to Dyndrite for making the conversation move forward, for facilitating the exchange of ideas, for bringing about amazing technologies. And we're excited to join the community. And happy to take any questions. Again, glad to be part of the community here. Thank you.
Great. Thanks, Blake. That was really helpful and informative. I think one of the things that's really interesting about having you here is we don't hear as much, I think, from the extrusion technologies as some of the other technologies at a lot of these events. And I was wondering if you could kind of dive into a little bit specific to extrusion technologies. What do you think is holding back production, and what do you think the sweet spot is for production using extrusion?
Yeah, that's great questions. Thanks, Kristen. So extrusion is a fun technology. You've got access to a lot of materials. You've got access to generally lower costs. The material formatting in terms of being a spool or sort of a roll of material is easy to store, easy to transport. There's low corrosion, there's low oxidation, there's low moisture uptake because the surface area is low. So there's sort of a lot of advantages with extrusion, but you're right. There have been limitations historically with extrusion in sort of factory context or industrial context. Predominantly extrusion machines have been very slow. There have been a very sort of small number of qualified materials. So, if you think about injection molding or compression molding or just molding writ large, there are thousands and thousands of qualified materials for molding, just for automotive alone. You see polypropylene with glass fiber and a UV compatibilizer. And this is just one example. The same thing with a polyamide or a nylon resin. With 3D printing, that type of material choice has never been able to come to the fore because historically machines have been really slow. So by unlocking the speed of the machine, there is now an ability to not only provide customer choice on the front end for the materials, but now clients where certification is a requirement can afford to certify new materials because you can get to a certification pathway much more quickly. So it's just, if you sort of think about what speed does for somebody, and this is one of the things that I'm excited to see more and more of with the Dyndrite software solution. I mean, like Harshil said, and others have said, the paradigm is flipped now. The machines are faster than the software or the software workflow. And so you start to have these machines that are no longer the bottleneck. Now it's the software or it's the user and helping them to extract the value from the software. So a lot of the solutions that you need for extrusion are at the end of the day the same solutions that are needed for a raster pathway type printing process, powder bed fusion type process, or sort of liquid resin type printing. You sort of need to compose the telemetry in the form of a vector or a tool path, which is slightly different math. But at the end of the day, by unlocking sort of, printing with splines and printing with directly from CAD and some of these things, then you can have ever greater machine performance, better part quality, and then customers are trusting more to turn to additive as a design solution. So we can all together get through this hybrid era. Like we've seen it, Sam was mentioning it, and it is a travesty when somebody else comes up and says, can you just print this part for me? And it was designed for molding or it was designed for machining. Yeah, I can probably figure out how to print it, but that's really not unlocking the value of additive at its core.
On a slightly different tack, it seems that you guys are working a lot with the military and multiple contracts with the Air Force. How is that influencing your view of AM, and what needs to happen to satisfy them with their scale requirements?
Yeah, so if you kind of look at what, this was really interesting. You talk about the open platform. It's not just an opinion that's held by Essentium or, as we heard earlier, SLM and other parties like Dyndrite. There was a paper written to Congress in 2018 where the CTO of the Air Force literally said in writing, the Air Force will only invest in technologies that allow material access. That is to say, open platforms. Full stop. So when you start to see government investment dollars that are being bounded by whether or not the governmental user has access to the material certification, the materials that the government user wants to use, you start to see there's going to be a paradigm shift in the industry. Because is the government use case the most predominant or cost-effective use case at scale? Not always. But the more the government adopts the technology, the more there are standards written, the standard agencies, ANSI, ASTM, ISO. These standards agencies are at the table with the government clients to make sure that they're getting what they need. And so when you see, again, this big push for open platforms and open architectures that allow that future of customer choice, that is heralding in a new era, and we're so excited about it.
I mean, we've seen obviously a lot of conversation about this topic of having open platforms today so far, even with Sam's presentation as well. I mean, outside, Do you have any further thoughts in terms of how that extends outside of the military, Air Force applications? Anything further more on the commercial side?
Oh, absolutely. So before I got into additive, I worked for Caterpillar for like 5 years. We put a factory on the floor, or put a factory on a green field in Central Texas. We had Mazak machining centers. We had like horizontal machining centers. We had lathes. We had grinding machines built by a different company. You had to have tooling in there from like Kennametal with like Mitsubishi inserts. We had Renishaw probes, and I think we had a Siemens MES. This is one factory in Caterpillar, which later, by the way, won a chairman's award for efficiency. We prided ourselves in single piece flow in the factory. We had a heat treat cell. We designed our heat treat furnaces and our heat treat cells to be able to have all different types of shapes of parts that could go through and get heat treat at the same time, because we were doing case hardening. So basically the whole point is, in actual manufacturing, you see Mazak and Kennametal and Renishaw and Mitsubishi and Siemens all playing in the sandbox well together. But Caterpillar is where the information resides on how to make the parts, on how to do the heat treat, on how to perform the grinding operations, on how to perform the machining operations. And that's what that type of mindset, is exactly where additive needs to be, embracing the customer more. Instead of trying to teach the customer, we need to be embracing the customer.
Mm-hmm. I mean, I think that leads really nicely into one of the last questions we have is, you mentioned cloud earlier. Is that meant to connect all manufacturing devices or just Essentium machines?
No, it's meant to basically facilitate machine-to-machine communication from Essentium machines to Essentium machines, but also we're excited to work on a machine-agnostic communications architecture so that Essentium machines can connect to other non-Essentium machines. If you look at semiconductor, there have been communications protocols like SexGem, Profibus, and others that were sort of somewhat adopted. Additive has never really had that kind of broad level of machine agnostic communication protocol. And I encourage my colleagues and my sort of community members here in the Dyndrite community, let's embrace together ways to allow our machines to talk to each other, or our machines to talk to CNC mills or CMM inspection equipment. This is how additive becomes a go-to in a factory environment.
We do have another question that just popped in. For what it's worth, from the automotive OEM view, we are taking this as well. Same goes for the slicer software. Should we have one system work on all the in-house printers, or do we have a very focused software for each printer to ensure the most hands-off operation?
I think that the most success will be found in an automotive environment as well if the workflow for additive manufacturing is similar to the workflow for subtractive. So in subtractive, you have like a Mastercam or Esprit or some other sort of, CAD CAM type solution. And then you have manufacturing engineers who go in and they create the G code. They use PostScripts. They use, extended G codes, G0 through G5, 5.1, etc. And that skill set defines whether you get great parts or whether you get parts slowly or parts quickly, to use a climb cut or a conventional cut, 3 fluted end mill, 5 fluted end mill, whatever it is. We have to get to a point where additive manufacturing software can provide that level of control back to the user, and they can have ideally scripts or script-based workflows, like, I don't know, maybe using Python or something. I mean, could make sense, right? So that you have that skill set and that expertise that resides with the automaker, and then they can go in and they can control their process, and they can nest the builds, they can select which materials they need, they can put the serial numbers in, they can do all the stuff that they need to do, but they can do it quickly. It's not being held back. It's not computationally slow. It's very, very fast. And the number of clicks that you need is minimal, and you can store the workflow and you can fly through it. And that's the kind of thing where I really think we're going to see applications at scale in automotive in particular.
That's awesome. Well, I think we could talk, your passion on this is clearly pretty strong, so we could talk about this for quite a while. But for now, I think we're going to wrap up the Q&A and we're going to move on to our next presenter. So thanks, Blake.
Awesome.
And up next, we're going to hear from Aconity 3D.
Thank you so much. Take care.
Well, now it is. Hi, everybody. Thanks for having me. And yeah, I'm absolutely delighted to be part of this DDC 2021 this year. And also, I'm really excited to have the opportunity to represent Aconity 3D. And Most importantly, maybe I would love to thank my preceding speakers. Blake, who pointed out that we need to work on additive manufacturing as one industry. I think that is essential to find new business cases, new solutions for customers, and make the vision of additive manufacturing in industrial surrounding reality. But also really important to thank Sam for his talk from SLM Solution. To me, it's really interesting to learn that SLM Solution is opening up, now has open machines architecture, because at the core, that is what we at Aconity 3D do for the last 7 years. And that is our DNA, that is our essence, that is what we wake up to do, what last thing we think about before we go to bed, providing new solutions to our customer. So let me try to take over the screen here. And it looks like it is working, I hope. Let me click again. Yes. So talking about open system architecture, which is sort of the topic of today, I would love to stress that, well, open machine architecture is core, is really important towards facilitating new business cases, because like Sam pointed it out, it's not us, it's not the machine makers who define solutions for customers, it's the customers themselves. And luckily enough, the whole industry now is mature enough that customers know how to tweak their process towards their needs, and they know how to take the most out of the process. So basically, all what we need to do as machine manufacturers is provide efficient tool machines which do exactly what the customers want to do. And in that framework, I would also love to point out, well, the software side of that. Hardware is one thing, software is another one. So today, DDC 2021 is data preparation. And I would love to put some focus on advanced exposure strategies and beam shaping for LPBF. So for those who don't know us, we at Aconity 3D are a machine maker for special 3D machines in the framework of laser powder bed fusion. So what do I mean by saying special? Well, what you see here is on one example of our Aconity MIDI system, our configurator, our truly open approach. Everybody can log on online at aconity3d.com, and customers can configure their machine towards their final application. So what we see here in the middle is our core Aconity MIDI machine as an example, and customers can now choose at the bottom what kind of preheating they might need for their material, because we learned about that today as well. Material development and making new material classes available for additive manufacturing is core and is really important, is key for new applications. On the left-hand side, you might then go ahead and choose some other options, just like the vacuum module for some die-hard material research, but also some separate process chambers or docking stations, which might help you to parallelize setup times. Then you can go further at the top and distinguish whether what laser power you want, but also how many lasers you want to apply. So that is basically an easy calculation for your specific application. For some applications, one laser is just fine. For others, you might want to use 4 lasers or even more in order to increase productivity. That goes hand in hand with the scan head you use. Y to the laser means 2D scan heads, maybe if you're looking into micro applications where really a small spot size is key for your part, being also small, but a really high detail resolution, all the way to 3D scan heads in which you can actually change or tune the spot size and also increase productivity, or multi-scan applications for multi-scan systems. All goes hand in hand with pyrometry, high-speed camera for inline process monitoring, but also thermal imaging for offline process monitoring. Everything is here held together with the Aconity Studio, which is our software suite, which allows you to sort of like a recipe, put together your hardware, control it with your software, and then feed it with data which is maybe prepared by Dyndrite or other data preparation software tools. And what that also allows is that customers can log into our Python API and actually control the machine without even needing our machine graphical user interface. So that's our interpretation for true openness. And that's shown here in our 4 basic systems. On the bottom right-hand side, our Aconity Mini entry-level sort of system, our Aconity MIDI family, which can have exchangeable process chambers for increased productivity or parallel setup times, and the Aconity One for larger scale full production approaches. And what I want to show here now are some examples what you can actually do if you have access to truly open machine hardware and software. And what we see here is an example, the video might be a little bit laggy, of magnesium. So what you see, there's so much fume, so much steam within the process, because the process window is rather small, that with standard machines, that cannot be processed. And what you see here is now we cranked up a little bit the fume extraction system of that system, and all of a sudden that becomes reality. So this is actually our very, very, very first Aconity Mini machine, which was provided to Fraunhofer IoT, who holds a basic patent in LPBF. And well, their goal was obviously processing magnesium. They succeeded in doing so, which we see on the bottom hand example, where we have this little scaffold, which is actually designed for being bioresolvable. So next example is micro SLM. I pointed that out. If you have true freedom of your hardware, you can easily just choose to have a really, really small spot size, maybe even modulate your laser, which will then allow you to do something like the stand with little wall thicknesses of only 32 microns with a material, in this case, nickel titanium shape memory, which is typically not available in the whole additive manufacturing landscape, so to say. So that is what motivates us every day. Other examples here, implementation of a green laser source. Well, we are an offspring of the Fraunhofer Institute for Laser Technology, so we believe that is our bread and butter business, so to say. So, of course, if you want to process different materials, you might need to change your tool of light. So in this case, what we did is we applied a green laser source, which then allows you to actually process pure copper in densities of above 99.5%. Another example here, high temperature preheating, not needed for every application, not needed for every material, but you as customers, you most likely know if you need a preheating or not. So in short, materials which are classified as easy to weld can typically be easily processed with LPBF. Materials which are classified as non-weldable, well, tough, they typically cannot be processed. What you can do here, in this example for titanium aluminide, you just heat everything up to well above 500 centigrades, and that allows you actually to print titanium aluminide really, really dense, more than 99.5% density, with the mechanical properties, at least the ones from the cast process. So now you can use these flexible hardware equipment or this machine to actually extend the scope of applicable materials and make your new applications reality. Another example here is, I hope the video works, multi-material approach. So this is, we have joined up with Aerosint in providing a multi-material recoating option for our Aconity MIDI Plus. So we see that here. This is a recoating process. And what we see here is copper and steel being provided on the substrate plate in X and Y. And now the information for the multi-material recoater is the same than the one for the laser, which we take. And so what we did here, take different parameters for different materials, and that actually then yields one of the first true multi-material parts built with LPBF. Sure. Or another thing, and now we come to the core of this talk, is switchable beam profiles. Means having flexible scanning strategies, not only from data preparation, that's what Harshil does, and that's what Harshil does really, really great, but also the possibility to change geometries on the system, not the geometries, but change the process parameters which you want to apply for your individual business case. So we want to give our customers the tool to develop their own unique selling point. And one selling point might be, I need to be faster, I need to be cheaper. So how do you do that? You might want to have faster melting processes. So one approach here is a laser source provided by Enlight, which is available or can be changed into different beam profiles. So you can start with your typical Gaussian beam profile, and for more bulky parts towards more productivity, you just switch towards a wing mode, which has drastically increased diameter while not having the overheating problem you would typically have if you would just defocus your beam. And here's a video. Please bear with me. This video is quite fast. I will play it again if it lets me jump to the next slide. Yeah, here it is. I will play it again. But this is to illustrate. In the middle, the core has been done with this AFX wing profile, while the surrounding more filigree structure will still be printed with a standard laser. And here for this titanium alloy, we were able to increase consolidation rate by a factor of 7 just by exchanging the standard laser, just by providing flexible hardware and allowing customers to work with that flexible tool. Next slide is here, our processing supporting lasers. So now if you talk about multi-laser systems, which are really, really fun towards increasing productivity, now even more fun is if you now define one laser to be the processing laser and the other one to be the supporting laser. Or maybe do that with up to 4 lasers. So here's a little schematic of what I mean by that. You can just have one processing laser and a slave, so to say, wobbling laser. You can increase a time offset. You can just choose a defocus around your process laser. Or if you have many, many lasers, just go berserks on it. And last slide here towards that is that we actually took a video from that doing our process with our high-speed process monitoring. So what you see in the middle in that video is the processing laser is shown here. And bear with me, it will slow down the video. And surrounding that processing laser in the middle, you see an 8-shaped supporting laser. Now it's a little bit slower, walking in 8. And if you pay attention real closely, you will even see that that supporting laser is in a wing mode. So that is the AFX laser provided in a wing to show what is possible here. And that is our approach towards flexibility, our approach towards providing tools for our customers beyond, or not beyond, but on site, what Harshil does with Dyndrite next to data preparation, has the flexibility to do what customers believe needs to be done for having their success story. So in short conclusion, aim of metals, well, full potential, in my humble opinion, not yet reached, but we try our very best. The whole community, the whole industry tries their very best to do so. We have a material choice which can be extended by flexible machines. Switchable beam profiles allow for even further trying to manipulate heating and cooling cycles of materials and allow for new material classes, and advanced exposure strategies next to data preparation can allow for full control, temperature, time cycles, and therefore, again, new materials, new business models on which we as a unified industry can work together. Well, thank you. That's all from my side. If you have any questions, I'm really, really happy to try and answer them. Thank you.
You mentioned Open Python interface. Does this mean you can basically program laser scan paths directly from a Python script? Do you have any interface with Python-based CAD software?
Actually, that's something
CCT?
That's something we did, and that's actually why I'm talking here today. Harshil approached us at one of these Form Next and said, well, we are brothers in mind, and you have a Python interface. We at Dyndrite have Python interface. So that's actually something we showed 2 years ago in the last physical Form Next, that we were able to not load only data like CLI format or the standard formats, but also load Python data from what Harshil provided to us with Dyndrite software. So in theory, that can be used to change geometrical data on the machine. Yes, but it can also be used. We have a customer in Sheffield to do offline layer-to-layer process control. So they just took all the sensor data, did their algorithms, and in the next layer, changed the parameters, all hands-off by using the Python API, which we provide.
That's great. Well, do you have any closing remarks before we head on to the next speaker?
No, thank you very much. I'm really excited to be part of this, and yeah, let's make this industry even greater. And yeah, see you on next events.
Awesome. Thanks, Yves.
Bye-bye.
Thank you, Yves. Now please welcome Technical Fellow, ExOne, Dan Brunermer.
Hello, everyone. I'm Dan Brunermer, Technical Fellow for the ExOne company. I also want to thank Dyndrite and all of the previous speakers. Today, I'm going to talk a little bit about something technical, because that's the kind of guy I am. And, you know, it's one of these things that we talk about in this industry a lot, death to the STL. And, you know, what does it mean? Whenever I think about this question, I think, what does it mean, obviously, for binder jetting, a truly voxel-based technology? And I'm going to talk a little bit about about both my skepticisms and my challenges that I hope to release some of my results by email. So I'm just, so that we all, and I know that this is a really smart crowd, but I'm just going to give a quick binder jetting overview. I mean, everybody knows lasers, but I feel sometimes like BJT still needs a little bit of explanation. I'm going to talk a little bit about what makes it unique. And then I'm going to talk about this aspect of voxels and the question I hope to answer. Just a tiny bit about myself. I will be celebrating my 20th year at ExOne this coming May 11th. I'm very excited about that. And I've been basically in heavy industry before that. Coming out of college, my first jobs were in basically, you know, automation, one-off machines, instruments, that kind of thing. So just a quick introduction to binder jetting, and I'm just going to make you watch this 1-minute video. I'll give you a little bit of an annotation as it goes on. So this is a machine in mid-print. And the first thing you'll see is that the build box is going to retract a little bit. The bed goes down. There's the recoding unit moves from the right to the left, and you're going to see like a little heating lamp. We have to dry off a little bit of that binder. It's very wet. You don't want it to smear all over your rollers. We put down the powder with this is our AAACT system. You can read more about it at exone.com/AAACT. It's a special way of compacting the powder and binder jet. You've got to have a really well compacted bed, and then you print the binder on top of it. That glues the parts together. I mean, that's essentially what binder is, right? It's glue. And what really makes binder jetting kind of special is that it's super high speed. It's really, now I know, hey, listen, there's a lot of companies that have gotten a lot faster, like Essentium and SLM and Aconity, and but binder jetting is still super fast. So I'm going to talk a little bit about outputs and applications real quick. I like to talk about how one of the things that's absolutely unique about binder jetting is that we can actually create 4 different product states by nature of the process itself. And we talk about bonded parts, meaning they're just simply glued together and they're ready to go. We talk about porous parts, where maybe there's a slightly sintered or some other process that turns it into a structured porosity. We talk about infiltrated parts. The birth of binder jet metal was actually stainless steel powder infiltrated with bronze, but we do a lot more infiltrations these days that are a lot more interesting. And then, of course, highly sintered solid ceramic and metal parts. And just kind of tying those product forms to some of our applications real quick. I mean, if you don't know, ExOne's like the absolute leader in binder jetting for the digital casting industry. And we also have a whole line of products now that are bonded that we use for washout tooling for composite parts. In porous structures, we actually did a project last year with Pitt and ANSYS and us working on a N95 printable copper, highly tortuous kind of a reusable filter. And then, with Infiltrated, as I say, that was the birth of binder jet metal. But now we have this whole line of EPIC tooling and parts that stands for engineered particulate infiltrated composites. And of course, as I say, we have highly centered parts where they can either be parts like what we've done with some other partners in the past, or of course, you can make solid tools with this technology because we can do tool steels. Okay, so voxels and binder jetting, and this is just kind of where I'm going to talk a little bit about the practicalities here of what I'm personally interested in and why I am personally using the Dyndrite engine and the voxelator. So I get asked all the time about what saturation is and how saturation works, and I've written several white papers in the last 18 years about it, and it's actually one of the key process variables that we identified in AMS 7022. That's an SAE spec on binder jetting. And, my point of this picture isn't actually to talk about saturation. My point is actually the very bottom picture where the part is broken up into little tiny boxes. That's voxels, right? And that is binder jetting, as a matter of fact. Now here I show it as like a very regular process. Delta X, Y, and Z are equal, but typically in binder jetting, that's not true. You might be printing at 400 DPI X, at 600 DPI Y, at 500 DPI Z. DPI, I'm sorry, meaning dots per inch. That's kind of like the industry common nomenclature is dots per inch rather than spacing or something like that. And the thing of it is, because it's voxel based, it means that, and in our case, it's a binary voxel based, meaning that that binder droplet is either going to be in that box or it's not. And it's a very binary situation right now. And I appreciate some of the thoughts that Dyndrite has about the future of binder jetting and what else we can do to control these voxels. But right now, I'm a practical guy, I'm a technical fellow, I'm a commercialist. And so this is kind of my reality, that I've got this fixed field of voxels and I can either make another one or not. But so what I want to investigate regarding STLs and voxels is, with binder jetting, this is a very highly relevant thing if I'm wasting voxels. The binder jetting, as I say, is really, really fast. And so when we talk about the scale of production, we don't mean the scale of production of an independent service provider. We mean the scale of production of a Ford, or a scale of production of some other big company that's going to be making millions of parts. And if you can save a couple thousand voxels on a part in a production application in binder jetting where the numbers are just huge, it really can add up. But I also, the way that this got started for me, I've been talking to the HP team a lot lately about the UBM, and I'm going to be a beta member, and I'm going to give it a try with the Dyndrite. But I wanted to try and think about, what does this really mean to me as a technical person, right? Because I'm a technical fellow, and certainly as a designer and as an engineer, I can appreciate things like tessellation and analog loss and, all these different things that we know happens with STLs. And I can dive into a literature review and I can find all kinds of scholarly papers that tell me all I could ever possibly want to know about vectors and normals and deviations from surfaces. But these all just kind of have been leaving me like wanting. I want to know exactly what we're talking about with these voxels, and should I care? Should my production customers care? And so I kind of came up with this really silly, simple test geometry that I'm going to run through the voxelator. And I'll go ahead and give you the punchline now that I'm halfway through that. And just as I was getting ready to start doing these tests and evaluations, I had a major computer crash, and I've been without a computer for like a week and a half. And so I'm hoping to have all of my data assembled and presentable by AMUG. But for today, all I can kind of tell you is about like the one practical, extremely practical, small, technical little question that I have been trying to answer for 20 years. And, does it matter? And, and I know now this is a pretty impressive graphic. I know I did this myself in Paint. But it's just kind of to try and show what it is that I'm saying, that, like we know that there's a difference between a circle and an approximated circle. And I know from my experience in STLs that generally the STL exporter is going to do something in a material safe manner. And I want to, and I just really want to know exactly how much excess material is there. And the Dyndrite engine really excites me a lot, because I really feel like I'm actually going to answer this question in a practical way that, just kind of has plagued me for forever. And for all I know, I may prove to myself it doesn't matter at all. But, I don't think that's going to be what I find at all. I think that whenever I go through all of the numbers, and, this part, I think it was like a 14 millimeter part total, so it means that you can print somewhere around 750,000 of them a year on a 160 Pro machine. So, and that's a rough number. I have to actually do the calculations, but, so the ability to save a half a gram on millions and millions of parts, that's like a really big potential. And I'm really, I think that it could be a bigger thing than we think, especially, when we talk about things like sustainability and efficiency and all those kinds of aspects. And so, yeah, okay, there it is. I did that in 10 minutes. Perfect. So yeah, here at ExOne, we have a vision of sustainable manufacturing without limitations. Unfortunately, I'm in front of a really smart crowd, so you know that there are in fact limits. But I'm really looking forward to working with this engine and with the universal importer, and really seeing what kind of difference can this make from our production customers, because I have a feeling it could be profound.
Great, thanks, Dan. So don't forget to submit your questions, but in the meantime, we do have one question for you. The presentation, you touched on STL versus the no STL debate. And I was wondering if you had an opinion on where you thought this was going to go, where this debate was heading down the line, and how, what kind of hurdles are we going to see, and how do they vary across various different technologies? Obviously your expertise is in binder jetting, but I'm curious if you can compare them.
Well, yeah, no, I mean, definitely. I think that, okay, I tell you what, I'm really not sure. And I took this to a person who's an FDM person, right? About, if you think about FDM, you're essentially programming a series of G codes into a machine. And so like there's G codes for doing interpolated moves, but there's also G codes for drawing circles. And so which is actually better? And I said, can't you draw a better circle if you use the G code for a circle? And his challenge back was, well, sure. But if you use the circle G code, you don't actually know your interpolation points. That becomes the business of the NC controller. So if you want to know how your circle is being interpolated, you're actually better off with an STL file. So, to me, now I think that's a little bit of a specious argument, but I certainly understand it. I think I'm going to find that for binder jetting, it's very important. And I think by extension for all of the voxel processes at speed. So, if I think about a company like EnvisionTech, a large scale EnvisionTech has the same CCs per hour as a ExOne InEvent Pro that we're releasing later this year. So I have to think even for them, like those are expensive resins, right? So if you can save even a percentage, a 1 or 2% of your resin in a production, again, if you're a one-off shop and you're, making 3 to 5 prototypes for a customer at a time and you're a service bureau, I honestly don't know how much the benefit really is. But if you're trying to really optimize the production of 10 million things, every single variable matters. That much I know from my time in heavy industry.
We do have one question also here, but I believe Harshil has a question he wanted to ask.
Sure.
I was going to say, Dan, I think that is a specious argument. Because you could also just have an open NC controller and know what it's doing, right?
Right.
That's not, that's an issue of the controller, not a general abstraction. But I guess my question to you is, right, like, I feel like a number of people will even say, okay, well, voxels are just another type of discretization, right? Compared to the linear approximation of a mesh, right? But the only key major difference here is the voxels are being done at the resolution of the print head versus the mesh. If you did it at the resolution of the print head, would kind of go astronomical in size, right? And would basically approximate a voxel anyway, right?
Yeah.
So I guess the question is, in order for voxels to kind of be that next order of magnitude improvement, right? Like instead of just cranking up the resolution of your approximation further and further up the pipeline, right? Do you think that there's an opportunity to just kind of use the print heads in a better way? I mean, it's a bit of a leading question because to me, if you change the droplet sizes.
Yeah, no, I'm interested to hear what Czar has to say, and I'm sure that some of my friends from Desktop Metal are here in the room, and I almost stole a picture off of their website to put beside my saturation one, which is a really interesting picture if you go look at it, because Desktop Metal does talk about how they do multi-drop. Right? Like if you go look at, I'm not sure if it's on the production system or if it's on the shop system, or not the shop system. I can't remember, but on one of them, they talk about doing multi-drop. But what you see is, even in their graphic, the droplet itself is stuck to that same XY spacing, right? Because if you have a 2D array of nozzles that you're controlling as an array, they all go at once. So, and you can do all kinds of creative things with printheads. Like, I use one that's got 8 different lines, and I can do all kinds of different things to kind of change up the timing and interpolation and whatnot. But at the end of the day, I've often fallen back on the vast majority of the parts that I have need straight edges somewhere. So I ought to put the droplets in a straight line.
Yeah, I think there's some clever opportunities here, right? To just kind of keep pushing, and I mean that's where I was going, right, with the print head side. It's, can we do more clever things to even go beyond the quote voxel resolution of the print head? I mean, of course you can always stagger and stack them, but can you get even more sophisticated with metadata, right? So.
Yeah, that's a good question. I mean, I think that there's opportunities. It's just, what I'll say is, right now, hey man, I'll be happy if I have a machine that can run, 200 hours perfectly in binary mode, which actually we do that all the time. But, like really, like having a good, stable super binary, even getting that stabilized for exactly one part, the numbers make that worthwhile. And what we found, I'm sorry, in my last minute, I'll just say that, in binder jetting in particular, it is in fact better suited for production than for prototyping.
Great. Well, thanks, Dan.
Very tunable.
We are a bit out of time. We've got to move on. So do you have any final words before we go on to our last presenter?
No, I just want to say thank you. Thank you for the time. Thank you for listening. And I look forward to tomorrow.
Great. Thanks a lot.
Thank you, Dan. Now please welcome Chief Technology Officer, Impossible Objects, Len Wagner.
Well, hi, everyone. It's great to be here today talking to you and taking up the caboose here on the discussions. I'm going to talk to you today about some experiments that we've been doing and Impossible Objects. We're trying to automate post-processing. And see if I can get... Okay. So just before we get started here, let's define post-processing. Post-processing simply is the work that's performed on parts after the printing process. This includes things like support removal, powder removal, resin removal, surface finishing, painting, coating, etc. Some of these things are additive, some of these are subtractive processes that go on there. And this is what I would call sort of the dirty little secret of additive manufacturing. We talk about the printing pieces and about everything's getting to be lower labor and faster and cheaper, but we don't talk about this. Problems with post-processing is it's a very labor-intensive process. We have lots of people with sandpaper and bead blasting machines and coating machines. So that's where a lot of the cost comes in, that it's manual labor. It's also, we run into repeatability issues because it's people doing this by hand. And really, we're running into a big problem here. We'd like to talk about the lights out factory, but that means that we're going to have a lot of people sitting in the dark for the part production here. So that just doesn't work. There we go. So we've been doing experiments at Possible Objects to see, can we reduce the amount of labor by, let's say, 80% on the post-processing. We're not done with this. It's not a finished solution I'm going to be talking about. It's more of a start of a conversation. And we're not trying to talk about solving everything. It's a very large and hard problem. And the thought is, if we can get the bulk, large part of the process done, then you still have people finishing up the 20%. But maybe your 40 to 60% of your spend can go down to 10% of your spend then, which would be a real worthwhile effort here. There are a lot of post-processing technologies out here already. Two main classes that I talk about is one of passive post-processing. These are things like, I'll call them dishwashers, but where you can use chemical solvent and agitation to run on your part. There are also things like tumbling systems. These tend to be simple and agnostic to your geometry. So they will remove parts, but you might have a portion where you have more material that needs to be removed, for instance, and it won't take it away, or a delicate part of your part which gets the same treatment as the less delicate parts and can actually cause the part damage here. Alternatively, there are active post-processing systems. In the corner here, I have a picture of a 6-degree free robot arm in a bead blasting chamber here. These will direct energy directed in a specific path to remove unwanted material here, for instance. What's nice is they do pay attention to the geometry, so you don't have that problem where you'll destroy portions of your delicate areas, and they are repeatable. The problem is these tend to use pre-programmed paths, so they're not feasible for low volume. And in additive, where we talk about mass customization and low volumes being one of the big benefits, that's obviously a problem because you can't amortize out that cost of that path programming. But if you think about what we are in additive is we always have a digital model of the part. And so the question is, can we use this to dynamically create the paths we need for post-processing? Not surprisingly, the answer is yes. The first step of it is we need to come up with a model. And this is the most complicated piece of the process here. But the model is going to be for the amount of material either added or removed. In this case, I'm going to talk about remove, or sort of abraded away per unit of time. You're going to have input parameters. This is a lot of the complexity here. This will be fairly specific to something like a blasting process here. You'll have the pressure from your head, the distance from the head to the part, the dispersal cone, so how large an area this of your beam is. You'll have the medium that's being blasted at, whether it's air or water or grit, the model material and support material. The output of this model, I'm going to call R here, is the material removed per unit area of time. So we'll say how many square or cubic centimeters per second that you'll remove. And because our materials are often anisotropic in additive, we also have to worry about the angle of attack, whether you're hitting it straight on the XY axis or at an angle may have a difference in your R value here. A simplified picture of what we're looking at, and you can get more complicated on this model. So you have in yellow rectangle for the blasting head here. It's got a dispersal cone in the orange flecked area there, and you're hitting at an angle theta. You're removing material there in trying to get towards your part there. Second step of it is you have to have your part registered in space so you know what you're hitting. This is probably the easiest part, luckily, but in this case, I'm just showing a datum point on a work holding fixture. A lot of ways to do this. You could use vision systems. You could, but the easiest thing is to use work holding. And then step 3 is using calculation of the depth of the material here. So I've got two depths that I'm worrying about. One is calling D1 here is the distance from the blasting head to this build block, the support material. And the second, the amount of support material here, the depth there that you're blasting away. Now, this is where we start to think of the word GPU. How do we calculate these distances? We have the geometry. We have the geometry of the build block, and we can use methods like ray casting or rendering and reading back from the Z buffer. If you did do a Z buffer, you'd have to render twice, once with the support material and once without. But luckily here, we can use these digital models and the fast rendering techniques to be able to measure these distances. A second extension we can do here is to create an active feedback loop. The models are difficult, but we can use them as a first estimate of how long to apply the forces to abrading away the material here. If we are able to put a rangefinder at the position of the blasting head, we can then measure the actual depth of materials and keep on blasting until we get to some tolerance within what we want of the part here. So while these processes are often dirty environments, so it can be difficult to do the sensing, if you can do that, that can be a simplifying factor and help increase the accuracies. As I mentioned, this is a perfect opportunity for the GPU. GPUs aren't just good for slicing, right? We can do it for wherever we need to be able to interrogate the geometry and get information on it. This is again an area where being able to differentiate with metadata between different materials, between supports, between models, etc., can be useful. And we can also, if we want to increase the complexity of this, apply various types of simulation techniques to get more complicated but more accurate calculations of how much energy to apply and where and from what angle. We are applying this to the Impossible Objects CBAM printer in our factory. For folks who aren't familiar with it, it's a industrial printer for doing composite materials, carbon fiber and fiberglass in particular. It's a fast printer with which produces strong light parts. And it's similar to a lamination process where we start with sheets of material. We then inject polymer powders to it, vacuum off the excess powders to just leave the slices, stack them up and press them and heat them, and then abrade away that uncoated portion of those sheets. So you can see how this would apply here. On the left, I have a Impossible Objects build block that hasn't been cleaned. This is what comes out of our pressing stage. In the middle, partially cleaned. And on the right, this is not actually a Impossible Objects parts that's being cleaned, but it's representative of our bead blasting process, what you would be doing in there. And the process that I'll show you here is basically automating this process here. Here's a experimental rig we've done, which was used for both measuring abrasion of material for nailing down our process parameters, as well as done for experiments on automated cleaning of parts quite successfully. I know this was fairly quick here, but I'll open up the floor to some questions. And here's some contact information if anyone wants to get in touch with me.
Great. Well, thanks, Len. We do have one question here. This is related to earlier in your presentation. How much of this AM process is process specific? For example, could cold spray be replacing SLM and powder bed fusion due to low post-processing costs, or FDM with soluble support versus SLA? Do customers balance material needs versus post-processing costs?
Well, the process that you use to create the part is going to be highly dependent on what your application of the part is, and what your tolerances are, what your material specifications, what your surface finishes requirements are. So with post-processing being such a large part of the spend, you are going to pick what technology you use to create the part. It's going to be a large factor in determining that, in your decision tree on what process to do. So yeah, I think over time, you have seen things like soluble supports, which were a great breakthrough to try to reduce the cost of support removal of parts, and where you can use an FDM part that's terrific. And so we have looked at, unfortunately, we have, for instance, materials that are chemically resistant. So it's hard to come up with the solvent, particularly solvent you want to use, where you could do a chemical removal. So metals, for instance, it's very common to have to remove the build plate and the supports and clean these things up. So yeah, I think you will pick what technology you use in large part for the total cost of the part, you have to include the post-processing for that.
Okay, great. Another great question is, what's the use case application sweet spot for your technology? And how do part costs compare to other processes?
So this is, I assume, for the CBAM process in general.
Yes.
So it's going to be highly dependent on the application again. What we find is CBAM tends to be more expensive per cubic centimeter than a lot of the processes out there. And you also have a fixed cost of build because you have the entire sheet being used regardless of how much of the part is in there. So we've got a lot of, if anyone has specific questions, we've got great costing models where we can look at it. It's going to be highly dependent on the utilization of how much space within that build block you need and what the specific requirements are. We do have a very strong part. So that our tensile strengths, for instance, are because of this long fiber component of our carbon fiber or fiberglass. We have half-inch to inch-long fibers, for instance, there. So you get much more like a hand-laid-up composite strength, but it's going to be highly dependent on your application. What we do find is on the applications where it's a good fit for the technology, the economic models work very well. But in general, we end up being in places where you really need the material properties to make it work.
Yeah, makes a lot of sense. Well, that's all the time we have for this Q&A. Do you have any closing words?
No, thank you, everyone. And I put the email at the end of the presentation, and feel free to contact me if there are any questions.
Great. Well, we're going to pass it back to Harshil now, and he's going to have some closing remarks.
So thank you all for attending a DDC 21 day one. It's been a pretty long day already with honestly quite a bit of information. You heard me talk about what we're doing. You heard a general theme about openness in the industry from Sam, Blake, and Yves. And then you heard us kind of start to really dive deep into the technical side of things with both Dan and Len, kind of trying to see and how we can push the limits of what's possible, and honestly, while considering the cost basis. So to summarize what we announced a number of APIs related to grayscale rationalization and isotropic offsetting, even more and improved GPU performance, and of course, the one thing that I think everyone was interested in, support-free printing. To give you kind of a preview of tomorrow, we have an entirely new and sort of different set of speakers coming back. We have Anthony Graves, head of software product and strategy at HP, giving the opening keynote. And he's at Cobra Moto and he's going to give a tour. So I encourage you all to come back tomorrow. We then have Sean Young from NVIDIA, and then Brent Stucker, Gareth, and Kevin from Ansys, Czar, and Aon, respectively. To conclude the day, we're going to have a fun roundtable with all of us talking. Given the amount of cursing you've probably noticed in our presentations, I have to imagine we're going to have a fun conversation because everyone is opinionated about what we're talking about. So to kind of conclude, I'd like to just put up a quick poll. We like to use these polls to honestly improve our shows and improve what value we're providing. If you could take a second to fill out which presentation or presentations you found valuable, that'd be most helpful. And yeah, I'd like to conclude by inviting you all to come visit us at AMUG in Florida this year. We're more than happy to show you and elaborate more on what we're doing, and excited to finally start to come and meet people again. With that, thank you all for attending DDC 21 day one. We look forward to seeing you tomorrow in the live virtual tour at Cobra Moto. Thank you.